All right, folks. Welcome to another series, another math series. This time I'm going to cover differential equations, one of the most fundamental subjects in all of mathematics. And it's one of my favorite math courses I've ever took. So um, let's actually get started about the overview of this course. So, a little bit of a backstory about differential equations. Um, well, what is a differential equation? In layman's terms, well, it's an equation involving derivatives, right? So here's an example of a differential equation, right? dy dx is equal to negative k times y of x, right? And k is a constant, okay? So our goal here is to figure out what family of functions would satisfy a differential equation like this. So just take a minute and try to convince yourself what would be a function which its derivative equals to itself. Do you know what such function? Well, it's the exponential function, right? So one way is we can let y of x equal to e to the x, right? Right? But since we have a constant kx, this will change a little bit slightly. So if I have it's just minus kx, well, it's just the exponential function, but your rate is not, and it's not e to the x, it's e to the minus kx, okay? Well, this solution would work, but also if it were multiplied by a constant, c, that would also work, right? So the family of functions that would work is if we have some constant times e to the minus kx, right? So e to the minus kx. So this is what's called a general solution, right? A general solution. Okay. So it's what's called a general solution, right? So this is part one of this goal here, to figure out a family of functions that satisfy a differential equation, right? And if you were to differentiate both sides, you'll get minus k times y of x. I meant y of x here. Let's see. Yeah, so this is times y of x. Okay, that's what I meant. And then sometimes you'll have an initial condition. So what that means is if we know a point which this function passes. So let's say, for example, y of 0 is 1. Well, that means, well, the x is 0 and the y value is 1. So we have to figure out a explicit solution of this form which satisfies a differential equation. So this is what's called an initial condition. We'll go over this much later in future videos, but all you do is you plug in 0 for x, and then this would be c. And this has to equal to 1, right? So our constant is 1. So our particular solution, which would be e to the minus kx, right? So this type is what's called a particular solution. Okay? So you might have an initial condition, and we would have to figure out an exact function, right, that satisfies a differential equation. And this refers to what's called the existence and uniqueness theorem of differential equations. We'll go over that much later. But that is the primary objective, right? And a little bit on history of where uh, this concept of differential equations came from. Um, the earliest discovery of differential equations um, actually was evolved during Galileo's time when he discovered projectile motion, right? And there's a typo here, but this should be d squared y dt squared equals to minus g. That's what I meant. Um, so this here is the differential equation that describes projectile motion, and it refers back to Newton's second law of motion, right? F equals m times a, right? Mass times the acceleration. Um, and with Galileo's uh, uh, projectile motion, the only forces that are acting on the object is, by assumption, gravity, right? So no external forces are involved in the object, right? So, um, so excluding like air resistance, this is a differential equation that models projectile motion, right? And to figure out a family of functions like this, well, so minus g is a constant, right? 9.8 meters per second squared. So we integrate this function right here on the left. So, and if we integrate it twice, we'll get what's called a general solution for projectile motion, right? So it will be minus g over 2 t squared. Um, Let me actually write this. Uh, oops. Can I erase it? Hmm. For some reason, it's not wanting me to erase it. Okay. Um, but anyway, let's just write it over here. I zoom out. So the equation for projectile motion, right? So y of t is equals to minus g over 2 t squared plus v naught times t plus s0, right? S0 is the initial height, right? The initial displacement, and then v0 is the velocity, initial velocity, right? So that is the what is called the particular solution for describing projectile motion, right? Projectile motion. Um, and really, I should mean x of t. Oh, now I can erase it. Okay. Really, it's x of t. Okay. So let me erase that. A small change here. Yeah, so this is yeah, so x of t. Gosh darn it. S of t. Okay. All right. And the this concept of differential equations was refined after the discovery of calculus, which was discovered by Isaac Newton. This here is Isaac Newton here on the right, and Gottfried Leibniz, right? And Gottfried Leibniz. And Leibniz. Okay. And you can see Isaac Newton's concept of differential equations in his paper, The Method of Fluxions, and his work on infinite series. So, yeah, his entire discoveries of his entire formulations of differential equations come from his book, The Method of Fluctuations. And then it was later refined. Can't erase that. It was later refined by Jacob Bernoulli. Oh, Jesus. And it was later refined by Jacob Bernoulli. With his Bernoulli equations. Let me actually write out the proper formulation of this. So it's dy dx plus p of x times y equals q of x times y to the n. Okay. So so we're differentiating y, and p and q are functions in x. So this here is what's called a Bernoulli differential equation. And it was proposed by Jacob Bernoulli, which is this person right here on the upper left. Okay. He was the first to propose this equation, and it was actually solved by Leibniz. And we'll go over the solution to a Bernoulli differential equation soon. But the other contributors to differential equations is Euler, of course, with Euler's approximation of solution curves for differential equations, right? We'll learn much later about the Laplace transform, which is named after Pierre-Simon Laplace. He was a French mathematician. So we're going to look right into Laplace transforms. And then also with Joseph Louis Lagrange, Louis Lagrange, French mathematician. His famous work was in second order differential equations, ODEs, ordinary differential equation. Okay, we'll go over the different terminologies of how we classify differential equations soon. And then there's many other contributors. These were the most famous that contributed to differential equations: Isaac Newton, Gottfried Leibniz, Bernoulli, Euler, Laplace. Okay, so this is a really exciting subject in math, and hopefully this will spark your interest into learning more about it. So what's really surprising is that differential equations come up quite often in real life. Um, so, for example, we can look at a differential equation modeling exponential decay. So we can use like this equation for carbon dating, right? Or looking at the radioactive decay of an object, right? Carbon dating, most common, they use carbon 14 to figure out the age of a artifact, right? Um, Carbon 14, this is just an isotope of carbon. What the heck just happened? Okay. Um, Sorry about that. So, yeah, so carbon 14, this is an isotope of carbon, right? And they use carbon 14 radiometric dating. Um, I think so I meant radiometric dating. Oh, Jesus. We'll talk about the textbook in a second. Um, Forget it. So, radiometric dating. Okay. So it's exponential decay if the constant k here is less than 0, or we can talk about exponential growth, right? So we can deal with populations of rabbits or whatnot. So mostly with the population of animals or bacteria or bacteria. K's so K is what's called the growth rate or decay rate if the K is negative, right? One of my favorite differential equations we can look at is what's called the logistic differential equation. And I know it's kind of wacky here, but uh, uh, it should look like this. So dp dt, this equals to, let me zoom in here, um, r times k times 1 minus, oh, shoot. Hold on a second. Yeah, I have to go to the actual size of the screen so I can erase all my writing on here. So it'll be r times p times 1 minus k over p. Okay. Uh, is that it? Um, oh, yeah. I'll wait. Okay, yeah, I've wrote that backwards. So let me rewrite this. So, okay, the logistic differential equation should be this. Should be 1 minus uh, k over p, right? K over p. So yeah, so this is the logistic differential equation, right? And so R is the growth rate of the um, is the growth rate. P is the population, right? At time t. T is labeled in years. K is what's called the carrying capacity, right? Carrying capacity. Okay, K is the carrying capacity. Um, and we'll talk more about the logistic equation quite often, right? And then where the population is at equilibrium, right? So where the rate of change is zero, right? In this case, the rate of change is at zero and the rate of change is at k, right? So if you want to figure out where a differential equation is equilibrium, well, it's where the rate of change, the derivative is zero, right? This is what's called equilibrium. Okay. It is also used in looking at the force of an electric circuit, right? Q of T is the charge of the capacitor in a circuit. L is the inductance, R is the resistance, and then C is the capacitance of the circuit. And then E of T is just some random electromotive force, right? So these previous two equations here, they involve a first derivative. Um, so we'll refer to what is called the order. The order is the highest derivative that occurs in the differential equation, right? So in this case, these guys are first order, right? Let me do a different color here. So this right here is a second order. ODE. ODE, this stands for ordinary differential equation. What is ordinary differential equation? It's a differential equation that involves one independent variable, right? If you notice in the first three examples, we only have one independent variable, so namely x in the population or decay differential equation. T was the independent variable for the logistic differential equation, also with T here too, right? And so once again, the order of a differential equation is the highest derivative that occurs in the differential equation, right? And then we'll deal with linear differential equations. I'll go over more of these definitions in the next few videos. So what we will not, we might probably discuss it, are partial differential equations, okay? So here is an example of a partial differential equation, okay? Well, namely, it's a equation that involves partial derivatives, okay? So it's an equation that involves partial derivatives, okay? So I'm going to erase some of this here because I want to just write out what this equation is saying. So this equation is supposed to be expressed like this. So partial of u with respect to x squared, its second partial of u with respect to x squared. This equals to a constant c squared times the second partial of u with respect to t squared. So this is a partial differential equation, right? It involves an equation with partial derivatives. So what this implies is that u is a function of x and t, right? So what this is called is the wave equation. T is the time, x is the location of a particle, c is the wave speed constant, and then u is the displacement, right? So u is the displacement of where that particle is in the speed in the string. Sorry, in the string. Okay. So these are just numerous examples of differential equations, how they um, model uh, uh, how it models reality, right? So it's pretty exciting. Okay, so the textbook, I'll leave a link for the PDF version of this textbook in the playlist description. But this is a great textbook. I think there's a new edition out, but nevertheless, there's very little changes in the editions. The most common is the sixth edition, Fundamentals of Differential Equations and Boundary Value Problems by Nagel, Saff, and Snyder. Okay, so the link in this for this textbook is in the description. The prerequisites. It's good to know that if you have Calculus 2, at least Calc 2. I don't think Calc 1's good enough. You're going to need at least Calculus 2 to understand most of this content in differential equations. It will be very beneficial if you take in Calculus 3. Okay. Because we'll look at much sooner exact differential equations, and they use concepts in calculus 3. And you may need some linear algebra content, but it's not necessary. We'll look at unique solution, existence and uniqueness of solutions of differential equations, and examining independent set of solutions, and it involves some linear algebra, taking determinants, and the Wronskian involves looking at an independent set of solutions, and that is the determining looking at the determinant of matrix of differential equations. Okay, so that is some of the prerequisites. If you take at least Calc 2, you should be fine. Calculus 3 and linear algebra content is optional, but I highly encourage that you freshen up on the content in Calc 2, most importantly. So if you're excited to be on this journey of differential equations with me, then let's get to learning. I will see you all in the next video. Best of luck.